Next topic in Chapter 9 is the ideal gas law.
All right, so we talked about our named gas laws, and the point of all of the named gas laws is to predict changes. I have a gas, I change its temperature, I change its volume, I change the pressure. How do the other variables respond? A different idea would be something that's called an equation of state. And the purpose of an equation of state is that it describes a single state of a sample of matter. So when I'm using the word state here, I mean like the conditions. Previously we had, say, initial and final. The equation of state would just be, well, what about just the initial? I want to know the relationship for all of the properties of that version of the gas. And so when we're looking at the equation of state for a gas, we could say, well, I have one version of the gas. What are the relationships of all the different variables for that? Okay, so for example, the kind of question that an equation of state allows us to answer is, if I know the temperature, pressure, and volume, can I determine how many moles are present? Okay, so these are different types of measurements that I'm now relating. And that temperature, pressure, and volume, those are the kinds of things that I can measure experimentally, right? Use a thermometer, you figure out the temperature, pressure, we have manometers or barometers, and volume, if you have a sample of gas, you can see how big the container is. But moles are potentially a bit harder to determine. Previously, we've measured the mass and converted that using molar mass. But if you have, say, a sample of gas, it's harder to put that on a scale, right? It's harder to put that on a balance and figure out what the mass of it is. So the idea of an equation of state is that we can relate different types of measurements to each other for one kind of condition that we would find our gas under. So if we're coming up to trying to figure out what sort of gas we can understand this relation about, we want to talk about an ideal gas. So ideal gas, first off, that word ideal means that this would be a gas that is ideal. It is perfect in some way. There are no ideal gases. So first off, we'll say that there are no ideal gases, but it's a good approximation for when we're talking about gases. And the approximation is that a gas is where molecules have no volume and there are no interactions between molecules. Okay, so that is our definition of an ideal gas. In a real gas, molecules have volumes, right? We talked about atomic size. There's more than one atom in there. They have shapes, all that stuff. Molecules have shapes, conformations, and volumes. But importantly, a gas has molecules being really far apart, so the molecules take up very little of the total volume. At the same time, molecules are bouncing around. They're just kind of jingling, moving really fast. They don't really interact with each other. If you put two molecules close together, they will interact with each other. But in the situation of a gas, they're moving so quickly, it doesn't matter, right? Who cares if the molecules are polar, for example, because they're just zipping around. They're not really spending time directly next to each other. They're not spending a lot of time close together. And the purpose of making this approximation of calling things an ideal gas is that the properties of an ideal gas can be related via this equation. PV equals nRT. So this is the equation for the ideal gas law. This equation completely describes the relationship for all of the physical properties of a gas. P is my pressure, V is my volume, N is the number of moles of gas, T is the temperature of the gas. This is a fairly straightforward equation, and it's going to be useful only for ideal gases. We are going to assume that any gas that we're going to deal with is ideal. Because if we just assume it's ideal, it's going to make our lives easier. This equation for ideal gases is much, much easier than it is for real gases. And so it's going to be useful just to make this approximation because we at least have, a nice gas. It's also not a bad approximation. Calling a gas an ideal gas is a pretty good one. You'll also notice there are no subscripts in this equation, right? There's no 1, no 2. We're only looking at one state of the gas, one version of the gas. What is the current pressure, volume, number of moles, and temperature? All that are packed in there. So then our final new variable is this capital R. Capital R is called the ideal gas constant. We have a value given here, 0.08206 liter atmosphere divided by mole Kelvin. So one of the things you see is that in the units, we've packed in all the other PV, N, and T. Everything is packed in there. And those units on our ideal gas constant are going to determine what the kind of units need to be for these values that we plug in, because basically we're going to want all of them to cancel out. You can change the units on your value of R, and the number will change. This 0.08206 only works for liter, atmosphere, mole, Kelvin. Generally, we're just going to use that value, and we're going to take our other variables. If we're given a different pressure, like say bar, we're just going to turn it into atmospheres to make our lives a bit more consistent. Not have to worry about a bunch of different values of R. Let's use the ideal gas law now. So, what is the pressure of a 0.041 mole sample of krypton gas that at 27 degrees Celsius that occupies 0.45 liters? We start by asking, what do we want out of this, right? What do we want to know in this problem? We can see that it is pressure. I want to know, what is the pressure? And so we want to think about, well, what do we have? What other variables are given to us? So we can see we got moles, we got degrees Celsius, and we've got liters. You will note that is an amount, that's a temperature, and that's a volume. You will note that none of these are pressures. Since none of them are pressures, what that implies is that this isn't a change, right? When we were dealing with the changes, if we were solving for, say, P2, we had to be given P1. But we're not given P1 here. We're only given we're asking for a single pressure. There's no other pressure variables given. That points to this problem is looking at describing a single state. And that means we're going to want to use the ideal gas law. Okay? There's no duplications of types. There's lots of variables, though. You'll note we're given a lot of information, but they're all distinct. It's a moles, it's a temperature, it's a volume, not moles 1, moles 2, like we would have seen when we were dealing with a named gas law. Whenever we're dealing with a single state, PV equals nRT is going to be our friend. We're going to use this a lot, get a lot of traction out of using this ideal gas law. All right, and now if we start with the ideal gas law, PV equals nRT, we always kind of just want to roll through all the variables that are in there, right? Because there's a lot in here and they're all unique. We know we want pressure, so in order to solve for that pressure, we would need a value for N, a value for R, a value for T, and a value for V. So R is a constant. We always can know what R is. We can always look it up, and we're going to have these units right here, liters, atmospheres, moles, Kelvin. And so if we take a look at the rest of the variables that were given then, we can note that the moles works out, the 0.45 liters works out, but we'll note that this degrees Celsius is not the same, just like we've seen previously. That needs to get turned into Kelvin. So this is going to become 300 Kelvin that we want to use in our calculation. Ideal gas law, named gas law, Boyle's, Charles, doesn't matter, always into Kelvin. So what we can do is we can take all those values and we can plug them in. And we can see that, moles and moles cancel, Kelvin and Kelvin cancel, liters and liters cancel. So that's why we always want to make sure that our units are in the correct value, that our values are in the correct units, right? Pressure needs to be in atmospheres, liters, whatever, to make sure it comes out with what we would expect. If we then enumerate everything, we get that the pressure is 2.2 atmospheres, right? So if we figure out, if we plug in everything else, we can determine that the pressure is 2.2 atmospheres. How about another? What is the temperature of a sample of N2 gas with the following properties? 0.28 grams, 380 millimeters of mercury, 150 milliliters. So we know when we're looking at here, we can see again, there's a lot of values given to us. What we want is temperature, and we're not given any other temperature value. Right? We're not given any temperature value, but we're given a lot of information. We got a mass, we have a pressure, we have a volume. All of those things are different aspects of a single state of gas. And so we're going to go ahead and want to use the ideal gas law here. We want to solve for temperature, so we can rearrange it, the PV over NR. But when we go to look at the variables, R, we're still given that, so that's good to go, 0.08206 liter, atmosphere, mole, Kelvin. But now if we look at pressure, well, we're given a pressure, it's 380 millimeters of mercury. So that's an issue because this millimeters of mercury is not the same as atmosphere. So we're going to have to deal with that. We can also see that milliliters doesn't match liters. We're not even actually given a moles. We're not given a moles sample. So the question is, how can we even figure out that moles and deal with all of those unit conversions that we need? So for the pressure, that can be a unit conversion. So millimeters of mercury, we can turn into atmospheres. We know that there are 760 millimeters of mercury. We can look up this unit conversion factor. Again, gases have, this kind of end of the semester, get some nice review as to how to do unit conversions. For the volume, that's a metric unit conversion when we're trying to go from milliliters into liters. That we don't have to look up. We can just know based off the prefixes that milli means you have 1,000 milliliters in 1 liter. And then to get moles, we can see that we are given a mass. So in order to go from the mass, which was 0.28 grams, into moles, we can calculate and determine the molar mass of our material. So N2 in this case is 28.02 grams per mole for N2. So the pressure, millimeters of mercury is a fine pressure. We just want it in atmospheres. Milliliters, totally acceptable volume unit. We just want it to be in liters, and we need our amount to be in moles, so that way we're going to cancel out correctly all of our temperature units that we have here. Or not temperature units, all of the different units in the ideal gas constant. Right? It needs to match up atmospheres, liters, and moles. So we can take those new units after post-conversion. We got into atmospheres, we got into liters, and we got moles that are here now. Okay, so we've done all those unit conversions. We can get everything set up. And so then when we go ahead, we can just plug them in to that T equals PV over NR expression, right? We got the P and the V, and then the number of moles and our R value. We can see atmospheres cancels out atmospheres, liters cancels out liters, moles cancels out moles. And so then what we're left with would be 274 and then the 1 over Kelvin. But we can go ahead and solve or figure that out. That just is the same thing as Kelvin. We'd invert it. This is a totally acceptable answer as this. The problem didn't give you a temperature, so you can just report it in Kelvin. You can also turn it into Celsius if you wanted. You'd get 1 degree Celsius here. This is relatively cold, at least as far as people go. And so you're at 1 degree Celsius. But Kelvin would also be acceptable. Either number works because they're the same temperature.
Question 3, participation 628. How many moles are contained in a 2.5 liter gas sample at 1.0 bar and 25 degrees Celsius? Third question for participation 628, due Monday, June 28th at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, how many moles are contained in a 2.5 liter gas sample at 1.0 bar and 25 degrees Celsius? All right, another video, another question. I'll see you in the next video.